Hello and welcome. Today we are going to talk about shifting stones, the shifting binary numbers. So last video we talked about negative binary numbers, which were represented by the leftmost bit. We've talked about sign magnitude, 1's complement, and 2's complement. And we covered overflow. Okay, we are talking about shifting numbers. And what do I mean by a shift? This is a 4. If you remember, this is the 1 spot. This is actually 2 stones. This is actually 4 stones. And this is actually 8 stones. So that's each time this is doubling. Each time it's a container that when the container gets filled, it doubles up and moves on to the next bigger container. It just completely empties out. Unless there's like 3, like on addition, and you have this, and it can only hold 1 at a time, but if there's an odd number, the odd number stays. So these 2 move over to here, which actually puts 3 in the container, but only 2 of them get moved over to the bigger one. So that stays there and that stays there. I just wanted to make that one clarification. But we are talking about shifting. So there's a fun thing where you can take this stone and just move it over. That is called a shift. And that. So the 1 becomes a 2, becomes a 4, becomes a 6, becomes an 8. Add a pencil, becomes a 16. Let's move more over. If we add another pencil. So we have a 1, a 2, a 4, an 8, a 16, a 32. Add another pencil. 64. Excuse me. And so on and so forth. But for simplicity's sake, let's just stick to that many pencils. So you can have this number, which is, let's see, what number do we have here? 1, 2, 4, 8, 16. Right? Yeah, 16. So 16 plus 2, which is 18. But we can shift, like when you're shifting something, you shift all the stones. And so I shifted this over, so this becomes an 8 plus a 1, which is a 9. So what did I just do? This was an 18, and if I shift it over, it becomes a 9. What particular math thing did I just do? This is a 9, and I shift it over, becomes an 18. I just doubled it. Because 9 plus 9 is 18. That is a powerful technique. So if I was to take the 9, shift it over, this drops off. So anytime you shift anything further than your bounds, like right now this is a 4 and a 1, this is a 5, you shift it over, just left with 2. And you can't shift that back. We're just going to imagine the stone just fell off into oblivion when we shift it over. That's an important mechanic for doing other things. That's not necessarily important right now. But anyways, so we have a 1. Now we have a 3. But if we move that 3 over, that becomes a 4 and a 2, which is a 6. So we just doubled that 3. And if we move that over, this is an 8 and a 4, which is a 10. Wait, right? No, 12. It's 12. That's 10, that's 12. So 12. 6, double the 6 becomes a 12. And if we double the 12, this is 16 plus 8. That should be 24. And the same thing is true with this. So this is 16 plus 4, which is 20. Shift that over. it becomes 10. We just halved it. We divided it by 2. And this is 10. Shift that over. This is a 4 and a 1. That's a 5. We just divided it by 2. And then the bit falls off, becomes a 2 because a 5. It can't round like a normal thing. So you're not going to get a perfect thing, not without floating points. And even floating points have problems. And we'll talk floating points. Floating points are its own bag of crazy. And it is complicated, and we will have to spend a lot of time dissecting what floating points are. But the long and short of it is, every time I shift that over, I'm multiplying by 2, or I'm dividing by 2. So let's say 5, 10, 20. 3, 6, 12. And then 24. Let's do 7. Let's do 7. So 7, shift it over 1. We are left with an 8, a 4, and a 2. So 8, 12, 12, 13, 14. So that's doubled it. And you shift it 1 more. We have 16 plus 8 plus 4. 8 plus 4 is 12. 16, so 1, 6, 1, 2, 2 is 8, 28. So we're left with a 28. And this is why binary can be so powerful. You can do mathematics way quicker if you're doing certain things with it. And there are a few things that are, I'll make that a whole other video, but that is shifting in a nutshell. There's one more thing to say about shifting. Let's say we are doing, there's such a thing as signed shifting. That means every time, let's say we have this number, and we want to keep this a negative number. So when you're shifting it this way, it doesn't matter so much. But if we're shifting it this way, we have to keep adding stones to the leftmost bit. So each time you shift it, you're adding it to preserve what this number actually is. So this is actually a -3. And if we were to shift it over, I believe that's, hold on, what is this number? So we have -3. This is, sorry, what was it? That was that plus that, which goes there, right? Yeah, becomes a 6. So I am doing this correctly. I just had to double check that. So what was it? We had -3. We shifted it over. And the 2's complement of this is this plus 1. This goes over, which is a 6, which is what we expected to do when we shifted a 3 over. And if we were to shift it once more, it's still negative. So let's add the 2's complement. And we add 1 to it. That gets cleared out. This gets cleared out and gets put to there. It's the same as if we were just moving these 2 bits, except negative. It still works. It only matters, you just always have to make sure that this stays negative. There's always a stone here when shifting to the left, but when you're shifting to the right, you add a stone. And if it shifts once more, you add a stone to that. So it stays the same number. And that, like unsigned shifting, you don't need to do anything. You don't need to add any more stones. You just keep the stones where they are, and you move them in relation to one another. And lastly, yeah, if you shift it and you keep shifting it, They just keep falling off when you run out of pencil spaces. And that is shifting mechanic of binary with stones. More videos to talk about. There is, why is all this important? And there's also floating points. We still have floating points to cover. All right, I will see you guys next time.